Hello everyone, and thank you for joining us for today's webinar, which will cover Vortex Cable Systems Developer. My name is Jean-Pierre Picard, and I'll be hosting the webinar today. With me on the line is Marc-Alexandre Vézina, our presenter for today. Marc-Alexandre is the product manager for Vortex Software Solution. So this webinar is part of the new Vortex University series of webinar. It's the first session that we'll be holding as part of the series, but it will now be a monthly presentation. Every month, we'll dive into a new Vortex topic. We'll go in depth with technical experts on the line, and we'll look at how to configure, how to create mechanisms based on the different modules and add-ons for Vortex. And we'll also do explorations of the samples provided with Vortex, how you can best use them, how you can learn from them. You can always see the upcoming webinars on the address displayed on the screen, and we'll also send you the upcoming sessions in the follow-up email. So before we get started, I'd just like to go over today's agenda. First, we'll look at the fundamentals of cable systems in Vortex. What are the parameters? What are the types of points? What are the types of cables that are available? Then Marc-Alexandre will do a live demo showing two use cases of cables in the Vortex editor and presenting how you go through each step to create them. And finally, we'll look at advanced cable simulation and the different options that are involved in there. At any point during the presentation, you can download today's slides on the handouts panel, and you can also use the questions box to ask any questions that you have. We have technical experts on the line ready to take questions as the presentation goes, and we'll have an open Q&A at the end of the presentation where Marc-Alexandre will take the most interesting questions and answer them verbally. So without further waiting, I'll let Marc-Alexandre get started.
Hi everyone, welcome to Cable System Fundamentals. Today we're going to look at how to implement a cable in the Vortex simulation software. The way we do a cable in Vortex is through a managed list of section and relax constraint. Resistance to deformation is achieved through the stiffness and damping of the constraint that compose a cable. We have an API that allows the user to easily parameterize various factors such as elongation, bending and torsional stiffness, damping, maximum allowed force and tension compression, and so on. All of these are set to match engineering parameter for ease of use. The cable system is located in the main Vortex toolbar under the icon cable. Once a cable extension is added to the Vortex scene or the Vortex mechanism, a property panel appears on the right side of the screen. Being an extension, cable system is managed via inputs, outputs, and parameter. Let's take a look at the inputs. The first on top is the active checkbox. Active signals the system that the cable needs to be generated and appears within the simulation. This is an input, therefore it's controllable via a script if you need the cable to appear or disappear at various moments in the simulation. Break now is used to signify to the simulation that the cable needs to break now. The break closest to section right under tells the computer where to break the cable. The next section is outputs. Outputs can be used to send information to a script or a display, such as the head-up display. It's useful to simulate stuff like LMI for a crane, for example. Information that's outputted is total length of the cable system, the current elongation, the maximum tension, and the maximum torsion. Underneath, we've got a section called Cable Parameters, which is further subdivided in three subsections. The first one is general parameter that apply to the entire cable. The second point is a list of points through which the cable will pass, such as a pulley, for example, or a winch. The last subsection is segment definition, which defines the properties of each segment between each point, such as being flexible or not. The dynamic parameter of the cable, such as stiffness and masses, are set via a separate extension that's called dynamic property. We'll take a look at it later. The cable system is defined via a series of points. Points are part of the same cable system where the cable is attached, spool, or its direction is changed. There are four different types of points: a winch, a pulley, a ring, or an attachment point. The points are added in the Vortex editor in the order of the cable path. In the diagram, you can see a winch, a pulley, a ring, and an attachment point. Segments are the segments of the cable that are located between the various points. They're part of the same cable system. Each pulley and winch define a segment of the type arc. The arc length is included in the total length of the cable. Other segments can be tuned by their definition. There are three types of cable segment. The first one is a rigid fixed length. This uses a massless approach. It cannot accumulate slack. It is rigid over contact if a collision geometry is defined for that segment, and the tension is transferred from point to point by a constraint called Vx gear ratio. The second type of cable segment is a variable length. It also uses a massless approach. It can accumulate slack, though it's not displayed, and it's rigid over the contacts as well. Tension is transferred from point to point by a constraint called Vx double winch. The last segment type is called flexible. It uses a lumped element approach, where each element within a cable is called a section. This captures most of the behavior of a real cable, such as slack, curves, mass inertia, momentum, and so on. It's non-rigid over the contact. It can be set to float. There is a way to set the buoyancy. The tension between point to point is transferred through constraint Vx cylindrical. By default, the cables are rigid of variable length, for example, between a winch and a pulley. Simulating flexible segment is CPU intensive, therefore it's better to set cable segment as rigid whenever possible. The CPU usage increases with the number of sections, so very complex cable are more computational intensive. Adaptive technology will help in case of a large number of sections. We'll take a look at it later. In this diagram, the cable from the winch to the first pulley is variable length, since the winch can add or remove cable. The segment length between the first pulley is fixed, since it doesn't change length, and the segment between the last pulley and the attachment point is flexible. Whenever there's a large number of segments, it gets very hard on the computer. It's very computing and power intensive. Long segment can have a very large number of sections. The adaptive cable simulation scheme simulates only the joints that are required to accurately represent the cable motion. Once sections are merged, it greatly reduces the computational cost. Let's go back to configuring point. There's four types of points: the winch, pulley, ring, or attachment point. Once we look at the property panel, there's a drop-down list that has the point type. A field right underneath is for part. This associates a part in the mechanism or the scene to that particular point. Offset is a way to offset the origin of the part where the cable will be attached. Radius is for winch or pulley. This is usually deduced from the first cylinder or capsule collision geometry found in the part, but can be adjusted later if need be. The inverse wrapping box sets the inverse of the wrapping from the one deduced by the cable system. It's usually used to fine-tune the pulley or the winch or the path of the cable. The angle is used only for the winch. It sets the arc angle through which it comes out of the winch. The relative primary axis is only used for the ring. It sets the axis parallel to the cable going through the ring. It's in the local space of the ring part. If we go in the segment section now, for each segment, we're going to define a collision geometry type, either none, sphere, or capsule. Note that this will override the setting at the parameter definition level. There's a box to support the torsion. If set to true, if the segment is to be constrained in torsion relative to the pulley or winch. Fixed point-to-point distance is true if the distance between the two endpoints of the segment doesn't change during the simulation. For example, between two pulleys. You can also set the fluid definition to true if the segment is to interact with fluids. The collision geometry must be set and the segment must be flexible. Drag coefficient for fluid interaction must be positive. Finally, there's a field for a buoyancy force scale, which allows you to fine-tune the simulation to account for the difference in volume between the collision geometry and the real object. Adaptive definition set to true will allow you to use the adaptive cable technology that we discussed earlier. Active joint budget will set the percentage of the total number of cable sections that can move with respect to each other simultaneously. Uniform subdivision is the maximum number of inactive consecutive segments. This allows you to fine-tune how much of the cable is awake and how much is inactive. In the advanced definition, the maximum active joint count is a hard limit of the number of sections that can be active at any one time. Maximum motion sample count is the number of sections that the computer uses to define the activity of an inactive region. Minimum acceleration velocity or threshold used to determine if a section is a candidate to be part of a set of active joints or not. And finally, the acceleration velocity coefficient or ponderation used in the computation of the activity of a section. This allows you to further tune how much of the cable is awake and therefore requiring additional computation. In the dynamic property extension, you'll be able to fine-tune and enter the physical property of the cable. These, as much as possible, match the real-world engineering numbers. The first one is relative elongation induced by the load in Newton, followed by the Young's modulus of the wire material, the cable diameter, the number of wire within the cable, the density unit used, either linear density or volumetric density, depending on the reference that are available to you for the cable, and finally, a feel for the density itself, which is the cable mass density. The first and last point of a cable will either be a winch or an attachment point. The intermediate point can either be a pulley or ring. This is set by the computer. If you try, for example, to put a pulley at the end of a cable, you will get a warning message. The cable will always touch the pulley. The cable will never unwrap from a pulley. If your simulation needs the cable to unwrap from a pulley for whatever reason, then that pulley cannot be part of the cable system. We'll use waypoints to have the cable pass through the pulley later on. Each pulley and winch assume that the mechanism contains part properly hinged. So for example, you'll need to have a part for the winch that's already hinged and properly set before you can create the cable system. In the usual, cable is better left for last once all the mechanism or the scene has been created and set. Note that when changing point definition, segments will be recreated. Therefore, if you change the point definition, you'll have to go back to the segment section to make sure that you haven't lost any tune parameter. Let's take a look on how to create cable within the Vortex editor. I'll be using the mobile crane that's found in the Vortex samples, as it's a good example of a simple mechanism that uses cable. The mechanism is already set with all the parts created, and I've already inserted a cable system through the cable tool up here. It's a generic cable. Catenary and pipeline, we'll look at them shortly. Now, if I go into the dynamic property, currently there's no point definition, so there's no cable defined. If we start the simulation, the hook will just fall on the ground. So we know that we have a cable that goes from the rear winch to the front pulley, down to this pulley, and then to the hook. So we need 4 points. So I go to the point definition section and I create 4 points. The first one will be a winch. So let's go into the assembly of the crane, and we go into the drum front. And the second part is going to be a pulley. Let's go into the pulley top. That's good. Let's go back to the cable and then get it. Pulley top. There we go. The second pulley is found at the pulley bottom here. And finally, an attachment point down here. As I said before, we can change the radius of the part if need be. So here I reduce the winch diameter a bit so that the cable will sink into the winch to get a proper physical look. Let's go into the segment definition now. The first segment is an arc. The second segment is between the drum and the pulley here, so it's not flexible, it supports torsion. It's not fixed point to point because we have a winch. The The third segment here is an arc definition over the first pulley. The segment between the two pulley is fixed point to point, and it supports torsion. Doesn't need a collision geometry. We have another arc section for the lower pulley. And finally, we have a section that comes from the last pulley to the hook. So we're going to set it to ball and socket attachment on the top of the hook, and we're going to put a collision geometry as a capsule, and we're going to set it to flexible. If we open flexible, and my preferred section are going to be smaller so that the cable flexes nicely. Let's try it out. And now we have a cable. Now we have weird behavior because I created a hidden part, which is a pulley, to show you a more advanced type of cable system. So let's take a look at it. We want to have a block and tackle system. So we're going to have to wrap that cable around that pulley and up here to the boom. So I've created a part here on the boom to attach the cable. So let's go back to our point definition. So we want to have 5 points this time. So it adds another point to the cable. So we're going to change the third one to a pulley, and we're going to change the cable to a pulley here. And then the last part is going to be an attachment point, and we're going to attach it to an anchor. There we go. Well, let's try it. And now we have a block and tackle with a pulley here and the cable attached up here. Now this is a fairly simple cable. If we go into the offshore sample that comes with Vortex again, which is one of our biggest sample, it includes an offshore scene that has a subsea and ocean surface with cranes and ships. In this scene, you can see another generic cable that links the TMS to the surface ship and uses adaptive technology to have a very long cable that's almost 600 meters long. We also have a second cable here, which is a flexible cable that goes down from the TMS to the rover. We have catenary cable here that are used to do the risers between the surface ship and the subsea module. And finally, we have the pipelines here, which do not move, but are actual pipe created with the system. So as you can see, you can create very complex mechanism using the cable system, and it's always the same procedure. One thing that I did not show is the graphic extension in the cable system. This allows you to have different properties such as cast shadow, receive shadow, have the cable visible or not, or transparent or not. These are all inputs, so they can be controlled by a script or a Vortex high-level interface. You can set the number of size, the radius, the graphic material, which will change the appearance of the cable. By default, the cable is going to be white with no texture. Let's go back to our presentation. Advanced cable simulation. Now, there's a number of advanced components that allows you to create a cable with a more realistic behavior. External damping is part of the main section definition. It can be activated to simulate fluid drag on a segment. It's a drag coefficient that represents the effect of the fluid on the cable. Note that this is a simple implementation that considers only the linear speed in the computation of the drag. This implementation doesn't require to have a set collision geometry for the segment, though the geometric radius is taken into consideration. Internal damping can be activated to avoid flexible segment instability. The maximum load that can be held by the segment without instability is entered here, and then the increased rate of the damping added to the original value is entered here. If the internal damping is enabled, once this maximum stable load is exceeded, the internal damping scale rate is going to be added to the original value. There is no effect on the damping when the tension is below the maximum stable load. The break cut cable feature can be used to trigger the breaking of a cable. Now, this was in the input. I've covered the break now and break closest to already. There's another section in the breakable parameter that allows you to have a break if there is too much tension on the cable. If this box is enabled, the cable will break once this maximum tension is exceeded. It's only exceeded if the maximum tension is above this number for this number of steps in the simulation. So this allows you to avoid having spikes in the tension that break the cable system when you don't want it to. These are part of the dynamic property extension. The cutting tool is a Vortex extension that allows you to model a cable cutter. The cutter field defines the part that is used to cut the cable. So you have to set a part in a mechanism or an assembly. If set to true, the tool is active and any cable will be cut when the specified part will touch the cable. The cutter part and the cable segment both have to have a collision geometry defined for this to work. Another tool is the waypoint tool. By default, the initial state of a cable is in tension with no slack, so it goes directly from the two ends of the cable. Flexible segments are created straight between the endpoints. So here, the cable would go from here to here as a straight line, even though it's flexible. If we use waypoint, we can shape the initial formation of the flexible cable. The waypoints are added relative to the mechanism if the cable system is added to a mechanism, and relative to the scene if the cable is added to a scene. In this image, there are 3 waypoints, one here, and one here, that allows us to get this nice curve in the cable. The number of points in their coordinate in the world frame of reference can be set by defining a size parameter of the point container in the cable's dynamic property. So in this picture, the waypoints are set in red and the projected cable path is set in green. Back to you, GP.
Thank you, Marc-Alexandre. So before we move on to the questions period, I just want to remind you that we've recorded today's session and we will make it available for download somewhere early next week. So we will be sending an email with the link to the file, and we will also include in that file the samples used by Marc-Alexandre today as part of the demo. You did mention that they were part of the Vortex 6.6 samples, but there were some modifications done to the mobile crane for the block and tackle demo specifically. You can download the presentation materials right now on the right-hand side of the GoToWebinar interface under Handouts. And you can ask your questions using the questions box. So before we move on to question, I would like to remind you that Vortex University is a monthly webinar series, and that next month's topic will be presented on April 7th, and it will cover Vortex Earthworks systems. In May, we'll talk about the process to transform CAD models into Vortex mechanism. So we will include links to register to both of these sessions in the follow-up email. If you are not staying for the Q&A session, thank you again for joining us today, and we hope we'll see you next month. All right, so first question for you, Marc-Alexandre. Do you need to use a winch in a cable system, or could you simply specify a total length for the cable?
At this time, yes, you need to use a winch at one end of the cable if the length of the cable will change in the simulation. Note that you don't have to have a graphical winch in your model. It's possible to just hide a part in the middle and use that as a winch.
Okay. Now, a question we have here regarding integration with third-party visualization products. You've shown the examples inside our own Vortex visualization engine. Can you integrate Vortex Cable Developer with third-party IG?
Absolutely. The way the system works, it outputs a series of points for the cable that can be sent out to another visualization software to draw the cable on screen.
Okay, great. So it seems the questions that we are getting are mostly related to specific mechanism. For those of you who have questions that are really about projects you're working on, send them to us. We will answer them, but we'll answer them privately by text. So we'll remain on the line. If you have any questions that are of general interest, we'll cover them publicly, but otherwise, don't hesitate to send us any questions you have. If after this session you want to send us any more questions, you can also email us at webinars@cmlabs.com and we'll get back to you shortly. For those of you who are leaving again, thank you very much for joining us today, and we hope to see you next month.